Well, hello everyone, and welcome to the second in the series of webinars that BHR is running on the theme of engineering innovation. In this series, we're dipping into and sharing some of the things that we have learned over the years while helping customers conceive and develop what they hope will be a successful engineering innovation program and ultimately product launch. In today's webinar, we will be focusing on some of the challenges that you may experience during early prototype testing and offer some advice on how we meet them. But firstly, really a confession. On reflection, the title of today's webinar, How to Succeed Where Others Fail, is a bit misleading because in the engineering world that BHR inhabits, failing during prototype testing is often essential to success. So some of the points we touch on today will be more about how you deal with failure to make a success. If you attended our previous webinar, you will know that innovation is a topic that is close to our heart. We know that it's one of the ways to continuously improve your products or processes so that you can address emerging customer or regulatory needs and so remain competitive. Innovation done well is one way that you can do this. However, it's also something that if you get wrong can be damaging to your business. In the first webinar, we looked into some of the things that you can do to maximize the prospects of getting your concept onto a solid development path. In today's, we will be looking into prototype testing, but I will, however, pick up on some of the messages from the first webinar that fit in today's topic. Again, if you're joining us for the first time and want to know more about what we presented previously, then you can request a link to the webinar video and we will send it to you when it's available. And finally, a really quick reminder of what we mean by engineering innovation in the context of these webinars. And this is a new idea that adds or creates value to a product or process. And by value, we're not limiting ourselves necessarily to only a financial benefit. Again, for a more complete description, visit our previous webinar. And so on to today's agenda. We're going to be here for about 50, I'll say that again, for about 30 minutes, maybe 50 minutes when we get into the Q&A, starting with me setting the context and presenting a three-step guide on the things that we have learned. These steps are not exhaustive, but a snapshot of the advice and learnings that we often need to use ourselves. That will be followed by my colleague Mark presenting a case study, talking about the experiences and learnings that we and our customers have gained. But most importantly, for you and us to get the most out of today, we'd really like to hear from you during either the presentations by using the chat function, and Kate's told you they're on the right, or in a Q&A session at the end. Today is all about what you take away, so please take advantage of these facilities. So just to reinforce, please use the chat and stick around for the Q&A. Please also use this chat to give us some feedback if you think these webinars are working or things which maybe you think we could focus on. We'd love to hear from you. And today is all about the actions that you take. So while a video of the webinar will be available, please use the time to make some notes as we go along. Very quick introduction to the team. I'm Jerry McNulty, that's me on the left, and I'm a business development manager responsible for developing relationships with key customers across the nuclear, renewables and defence sectors. I'm joined by a couple of colleagues. Firstly, Mark Fairhurst, shown in the middle. Mark is one of our senior consultants and a specialist in high pressure engineering and fluid power systems. Mark's been involved in many product development programs, providing valuable expert engineering consultancy advice, but this balanced with pragmatism. And this has really helped our customers turn concepts into viable engineering solutions, and even more importantly, compelling business advantages. Mark will present a case study from which we hope you'll take away some valuable insights. In the background, keeping us under control and managing the chats is Kate, our marketing manager. So again, thanks both to Kate and Mark for working with me today. I think it's really important you understand where BHR Group fits into this engineering innovation process, and also why we're able to talk on this topic from a position of some authority. So a short recap on who we are and what we do. BHR Group is a specialist engineering consultancy business based in the UK. Our expertise is in the application of fluids engineering to solve problems for industry, and we've been doing this since the 1940s. Now, fluids covers an awful lot of engineering disciplines, and so we're really in a privileged position to work for many industrial sectors, and there's quite a few of you on the call today, each with your own needs, challenges, supply chain standards and so forth. Well, what that gives BHR is a really good opportunity to understand various engineering and business demands and really to adapt our know-how in a safe and effective way to meet them. As experts, we see the greatest benefit that we can offer you is to understand, quantify and mitigate against engineering risks in your business. And prototype testing is really a key part of that. In general, we do this risk understanding a number of ways, which includes providing expert-led advice and insights, engineering designs, including modelling and simulation. This is all supported by in-house R&D services and specialist testing. And all of this allows us to develop, test and adapt innovative products from lab to near full-scale demonstrators, but under simulated lab controlled and so risk control conditions. This really puts us in a really good position to develop and build long-term relationship with both equipment suppliers and end users. And of course, we can use this experience and learning to work with our future customers and also more widely through events such as this. So I hope that this gives you some appreciation of what we do and also gives you some confidence that we know what we're talking about. Now that we've set the scene, let's jump into today's event. And I'm going to start by talking about the 3 things you must do to succeed where others fail. But before that, let's understand where we are. Now, you may remember when we talked last week at concept development, we've now moved on some time from that. It could be months, it might actually be years. But what this does mean at the start of your prototype development testing, you should understand the engineering requirements and challenges. You will have previously written something like a product requirements doc to allow people to understand what a product should do. Well, by now, this should have been expanded to define how the product will do it. You'll also have a prototype, something with a shape, size, feel, and which is properly integrated with control and measurement systems. You'll have developed relationships with your project team and the customer. And finally, that all-important matter of financing or securing internal funding will remain an important focus. So with all of this in mind, let's move into today's advice in 3 must-take steps that will help you navigate your way through the prototype testing phase. As I've said before, these aren't exhaustive, but a snapshot of the advice and learnings that we often have to use ourselves. Now, one of the first key steps is not a technical one, but it is to recognise that there are different agendas within your team, and you've got to understand what these different agendas are. This is especially the case where you're working on collaborative projects, which is a common approach these days as projects get more complex and therefore you've got to integrate more skills. Collaborators can typically include academics, developers such as BHR Group, OEMs and end users and so on. And even if we're all on the same song sheet, you just know that sometimes you're interpreting the music differently. So for instance, you may have someone in your team who's been with you from the beginning and so is motivated for personal career goals, or you equally have someone for whom the job is just a 9 to 5. Both, if they apply their capabilities correctly, have a part to play, but their drive and motivation puts them in different places on the team. Knowing this, we need to make sure that each collaborator is interested and invested in what the other is doing. And by understanding what these needs are, you can then work better as a team. To do this requires more than working up a well-structured project plan or product lifecycle plan with clear descriptions of the tasks, deadlines, milestones, and so on. But don't get me wrong, these are needed, but as importantly, you need to build your team, and this will be a greater challenge when you're either not physically together or you're actually seeing things differently. You've got different perceptions. So I guess what I'm trying to say is that just like in engineered systems, it is at the interfaces of the collaborators' different interests that you may find frictions and difference of opinion. So you need to think about how to lubricate these interfaces in your team to make things run smoothly. An example of this approach would be for an industrial partner to fund or sponsor a student of an academic partner. That means you're working, looking at each other's interests. Or for the IP being developed by one partner and diffusable to another to be made available at a beneficial commercial rate. So this is all about how you invest in each other. We've seen these kind of arrangements work on collaborative projects before. And finally, preconceptions are based on hope and opinion, and these grease the wheels of expectations. You need to move these to goals which are concrete and based upon reality and fact. As engineers, we need to be squarely in this latter camp, which brings us back to the requirements document. Yet even here there can be mistakes. If you remember from the last presentation, I mentioned about asking the right kind of questions of the customer. Well, at BHR, we've also learned that the customer also needs to ask the right kind of questions of themselves. And this can arise when the technical information being reviewed by the development team doesn't stack up or where it is not properly understood. So, as developers, we mustn't assume that all of the information we receive is correct. And therefore, we mustn't assume that we're mistaken. Our experience is that our customers respond well when we ask for clarifications, even if this throws up potential problems for them. But of course, you should have a formal process in place to manage these kind of activities. And this leads us into the next learning, which simply put, and I'm not going to go through that title, but simply put, it is to state what you don't know and find somebody who does know. We sometimes find that customers can have difficulty fully describing the features and functional requirements of the product that is being developed or the application environment in which it will operate. This can be complicated by the customer leaving out important information because in their mind it's either obvious or unimportant, and neither might be the case. And finally, another reason for these unknowns is because of the size and structure of companies, and where it might not be easy for them to get the information that you need. So what can we do about it? Well, just like in the X-Files, if you remember that TV program, you will be better off having someone in your team who can dig out the hidden information. We've found that one of the most effective ways to identify and address incomplete customer information or information that might be in conflict is to get a representative of the customer embedded into your team. Even if only on a part-time basis, having someone who knows what to look for, where to look, or knows who to ask is a really productive way to address these kind of issues. They can also act as a conduit between the development team and the OEM or the end user. And we have found this to be particularly helpful if this someone has a different mindset, as they will interpret this information in a different way to us. And so they can also challenge our preconceptions and expectations, and you get a kind of virtuous circle. And all of this helps us identify the constraints. Now, we all recognize that engineering is about working with constraints. At an internal project level, this means managing time, the availability and capability of resources, and so on. And you'll have a suitable project development process for these. But you also have to understand the external constraints, as the regulatory environment, partnership, contractual environment, maintenance expectations, and so on. So knowing the constraints is good, as it gives us direction, focus, and purpose. The prototype testing phase is all about confirming the known engineering constraints and identifying and addressing the unknown ones. Now, some of these will be teased out during the testing, which I'll come on to. I've also touched on commercial contracts in the discussions, as this is something that also needs attention, as the role of partners and even the the makeup of partners, the nature of the risks, liabilities and so forth will change through the project. So no matter where you are in the development programme, my advice is to put a fit for purpose contract in place and change it as circumstances demand. If things go wrong in the development of your relationship with partners, and they can, you don't want to be locked into an unacceptable contractual terms, as ultimately this only benefits the lawyers, and we want to keep the money in our pockets and not theirs. So, in a development programme, what you know is often less relevant than what you learn. And as I presented in the first webinar, knowing the answer to questions is less critical than having the ability to ask the right question in the first place. In the process of defining and running prototype tests, we have sometimes found that the focus of the testing is wrong or incomplete, and that new factors become important. So we need to understand the significance of potential consequences of this new information as it arises. We all understand the need for honest and informed feedback with your customer and other partners, but this can sometimes be a difficult conversation, especially if it involves asking for more money or moving budget from one activity or partner to another. And so we definitely see the value of early warning processes such as risk registers, and on all the development projects we work, we have one. I'm not going to dwell on failure, but we do need processes that will give meaningful and constructive feedback, even if it is bad news. On the latter, we know that it is hard to improve on anything if you're unaware of the limitations or your limitations and make poorly informed assumptions. So to sum up, step 2, in the words of Gene Kranz in the film Apollo 13, work the problem. Let's not make things worse by guessing, or in our case, making assumptions. Which really leads us into the final of today's learning. Having addressed the challenges in steps 1 and 2, you will now have gathered a raft of competing test requirements, and most likely you will have to optimize your test program to fit within a budget. If this is a first-of-a-kind test, then unless you have an in-house R&D capability or access to a test house, this is going to be difficult for you to understand and difficult to budget for, as you've got no real feel for it. So you have to have people with experimental testing skills, in which case you'll be in a good position. But if you haven't got these, you need to look for them. A good approach at this stage is to really discretize or uncouple the requirements and the challenges. You may remember that the requirements doc I mentioned earlier will have specified what the product is to do, and the test program is needed to demonstrate this. But in addition to this, you need to consider a few other things, including how to meet industrial standards, and if it fails, you will want to know how and why. We find that a cost-effective way to planning for prototype testing is to break these requirements into their component parts, or uncouple the different physical and or other test requirements into separate challenges, and where practical, test at that level. This will help establish what the cause and effect mechanisms are likely to be, and so give you enough engineering data for you to understand why the product is behaving as it does. Numerical simulation and modelling can really help, as it identifies where the largest uncertainties are and really where you need to be focusing your testing on. Once you've decided what you need to test and why, you need to consider how. This should be a scientific or a systematic process and not guesswork or intuition, although the latter, if based on experience, can be helpful, but it's not everything in itself. To run an effective test program usually involves compromises. This is even the case if you have the test facility. Now, compromises when collecting test data usually mean that your results will have uncertainties. And as engineers, we need to be clear on what these uncertainties are. So just as we accept tolerances on the fit of mechanical parts, we need to specify and measure the uncertainties in our tests. This should be part of what you do to optimize your test program so that you can capture the maximum range of data with the minimum uncertainty. And we typically do this by taking a design of experiments approach. The aim of all of this is to put data points on expected trends in a systematic way so that the results can be interrogated. With this in mind, you can now run your test program. Design of experiments is a powerful way to structure your testing and can be separated or coupled with other important techniques for optimizing this test program. This includes factors like agreeing the scale-up criteria, which simulants you're going to use, the range of test parameters to consider, and so on. This approach is particularly useful during early stage prototype testing, where you're gathering knowledge and where our experience is that even simple tests can throw up unlikely results. So you need to keep your tests simple and flexible, and this is more achievable by testing at a smaller physical scale and under simulated conditions. It's a truism that you learn more from failures than from successes, and quite often our test work involves making things fail or testing to destruction, but of course this is under simulated and controlled conditions. So to understand the failure mechanisms, we usually start at a relatively simple level and grow in complexity and get more integrated with each successful test campaign. This can also help in deciding if and when to halt a development, which will be easier if you have not yet invested in a complex test program or test facility. But of course, prototype testing is also about understanding the world of your customer. And so this phase of your product development is a great opportunity to feed back the important findings of your work and use this to build your customer network by engaging with other key stakeholders or influencers. When you're ready, find a way to get them directly involved with hands-on experience with the product or equipment. The example that I'm showing on screen at the moment shows photos of a development where we're developing a fire suppression system. We took the early prototype, shown on the left, to fire departments around the UK and Europe, and let firefighters play and test equipment in different operating scenarios that they set up. So we didn't control that element. Their feedback was invaluable in setting the next stage in the product's development, and of course we got some buy-in from the end users. So there you have it, our 3-step guide to help you get onto a successful prototype development path. With that, I will now hand over to Mark, who will share a case study. Thanks, and over to you, Mark.
Thank you, Jerry. I'm going to share with you today some experiences that we have had in a project for Magnox at Berkeley, as it highlights the benefits of making prototype. It involves our high-pressure abrasive water jet cutting process called DiaJet. In 2017, Magnox approached BHR Group to discuss a particularly challenging task at the Berkeley Nuclear Power Station. The Berkeley Power Station has reached the end of its operational life and is being decommissioned through a phased program lasting several years. One challenge facing Magnox was how to safely remove intermediate level radioactive waste from the site and put it into long-term storage. There are underground waste vaults at Berkeley with steel canisters that contain radioactive sludge. This is backwash filter sludge from fuel storage ponds and other facilities dating back to the 1960s. There are over 1,400 sludge canisters at the Berkeley nuclear site, and the radioactive sludge contains microbial activity which has generated both hydrogen and methane gas. Over the years, this potentially flammable gas has caused the canisters to become pressurized and thus even more hazardous to remove from the vault. The original idea was to take the canisters out of the vault and drill a hole in them within an enclosure. However, a safer solution was thought to be to depressurize the canisters whilst they were still within the vault, but this would require a cold cutting process such as DiaJet. As an alternative to the current approach, we would have to prove ourselves every step of the way. It was important that we started small and worked our way up to what was going to be a remotely controlled and fully integrated system for Magnox. We first had to prove to Magnox that we could indeed pierce the canisters using Diajet, and then this would allow the flammable gas to escape in a controlled manner without detonation. Calculations had shown that the hole needed to be less than 2 millimeters in diameter, or the gas could ignite by deflagration. As we found out later, the hole needed to be on the small side to start off with, as the escaping sludge could erode the hole during the depressurization process. Magnox told us that they also had to verify that the canisters had indeed been pierced before they could be safely removed from the vault. We originally expected to use CCTV, but our trials showed that this visibility could be compromised, and that led to a lot more work to find a robust solution. This again would not have been obvious without the trials. Finally, as with any safety critical application, we had to make sure that the process was repeatable and reliable, and that meant using a sequence that would run through time and time again without fault. Building prototypes and models and testing in a simulated but safe environment is key in the development process. It allows flaws to be detected early and corrected without drama. But as Jerry mentioned, to the point that we understood the key factors, the known unknowns was a challenge itself, as there are other considerations and constraints at the Berkeley site, and more specifically within the vault. As I mentioned, seeing what was going on was one of them, but just as important was the escaping gas and how to manage it safely. As was touched upon in the 3-step guide, we like to do quick and simple trials on smaller subsystems or at a component level, as this can reveal other limitations, not necessarily of the application environment, but of the product itself. So before we put our thinking caps on to designing the cutting head, we did some brief trials to optimize the jetting parameters needed to pierce the canister lid. This indicated the choice of nozzle and the operating conditions, as well as gave us some information about the piercing time and the quantities of water and abrasive needed for each pierce. It not only defined the jet nozzle and the holder, but the reaction forces that fed into the eventual design of the cutting head. Of course, the cutting head had a list of additional operational requirements from Magnox. It had to be deployed through a small opening in the vault roof. It had to be free enough to move so that it would not damage the manipulator holding the canister. It had to engage with the canister lid firmly to simplify positioning for the operator. This required not only attention to detail, but working within the physical constraints of the vault. We also were constrained by limited vision or views of the operation and the limited remote handling options and so on. And so we built a mock-up of the vault at BHR and made some dummy canisters so we could explore the practical boundaries of how the manipulator could be used to attach the cutting head to the target canister. Simulating the movements of the manipulator on a hydraulic trolley allowed us to practice our methods of attachment and help generate procedures for the operators. Using CCTV to mimic what the operator would see from the control room helped refine the procedures. Getting to this point was helped by having one of Magnox's external contractors work closely with us. Not only did he act as their technical authority, but he was able to pull in other key personnel as necessary through the development and test program. In many ways, he acted as the product champion. I'm sure that without his involvement, we would have missed opportunities or misinterpreted some of the information provided to us by Magnox. I stressed in the previous webinar the importance of communication, and so I make no apologies for stressing it again here. Getting to know the customer and their challenges is important to providing the best solution and the quickest path to it. The prototype trials were initially driven by the technical requirements, as each element would need to be proven. Simple things are tested first and any problems corrected before moving on to more complex tasks. Some of the tests are clear-cut, pass or fail. Others need to be repeated to prove consistency. It's also fairly obvious that you're going to test on air and water before moving on to messy sludge simulant and helium gas. Having the customer there doing the trials saved time and money, as well as made quick decisions and kept the tests relevant. The first trials looked at deployment of the cutting head through the vault penetration, and then the fit and alignment of the cutting head to the canister. The dummy canisters were made as pressure vessels, so they could be filled with water and the sludge simulant to investigate what happened when the jet pierced the can and how it depressurized. Everything of importance was instrumented and data logged. Jetting trials proved the stability of the cutting head during the piercing operation, but just as importantly, enabled us to build up experience of the whole piercing operation. Also, as an SME, we learned that the processes for checking, reviewing, and approving all these stages were understandably very rigorous. This is a steep learning curve for smaller organizations who don't necessarily have or need the same level of document control and other quality assurance requirements in their non-nuclear work. However, even though this experience was sometimes challenging for us, it helped by having one of the Magnox team with us to guide us through their processes. It was from the prototype head and mock-up that it became obvious that we would need to develop a second method to verify the can was pierced, as the CCTV image was not clear due to the mist around the water jet. This led to the development of an acoustic method of verifying the pierce and depressurization of the cans. So we added microphones to the cutting head and some noise software on a PC to prove the method. It was also obvious from the prototype trials that any gas escaping from the canister could collect in the roof penetration, which could potentially build up above the minimum explosive limit. We repeated the trials using helium in the canister and measured the gas concentrations at various locations within the mock-up vault. And this led to the addition of nitrogen gas jets to the cutting head to assist in the gas dispersal from the venting canisters. Again, this is one of these consequences that Jerry mentioned, and which testing revealed, and it got even more complex. The noise from the nitrogen gas jets interfered with the Pierce acoustic signature. Basically, we couldn't hear the water jet over the gas jet. It took a while to figure this one out, but we ended up putting the nitrogen gas through a high-pitched nozzle with a discrete frequency range above that of the water jet. We could then look at the frequency spectrum of the water jet without the gas jet interference to verify that the pierce was indeed okay. As I said at the beginning, testing the prototype in a good representation of the final installation teased out lots of problems, flagged up things we were not expecting, and significantly increased the chances of a successful final installation. For most of the early prototype cutting head development, we used an existing portable diajet system that we had developed for the military ordnance disposal. I'm going to talk more about that next week in our final webinar in this series. However, using existing equipment helped us identify the specification for the fully automated system, and that enabled us to supply a cutting head system with high pressure abrasive and water outside of the vault building. So the final solution was a containerized system operating by remote control from the vault control room that sits alongside the operator handling the canisters. A supervisor has the noise signature recording on a separate PC to help verify a successful pierce of the canister.